Okay, so we learned about Bohr models the last time. Today, we are going to take the same idea and apply ions to it. Okay, and this is where your isotope notation is going to change slightly because now there is going to be a charge value. And that charge value is going to show you what happens to the electrons that would normally exist in the outermost shell of your atom, but something has changed, right? So, or not something has changed, but you're changing what's happening to those electrons by adding this C value, this charge value, right? So if you had a positive charge, you are removing electrons. If you had a negative charge, you are adding electrons. So let me make that super clear. If your C is positive, then you are removing electrons. If your C is negative, then you are adding additional electrons, right? Because you're shifting the charge balance, right? So we know that a neutral atom, let's do a really easy one. Let's go to our periodic table. What's easy? Let's do hydrogen. Why not? Let's just do hydrogen. We'll do hydrogen. Okay. So if we do hydrogen here, we'll take hydrogen and we'll say, okay, hydrogen has an atomic mass or a mass number of, wow, of A, of one. Hello. It has a, excuse me, atomic number of one, which means it has one proton, right? And it normally has zero neutrons. Now, we also know that according to this, if there's no charge at all, then it must have one electron, right? Because the negative value of the electron needs to cancel out the positive value of the proton. Okay, great. Now, here's the deal though, right? We want hydrogen to be happy, to be without this extra electron, basically. So let's let's take a look at what this looks like, right? So let's look at the model. If there's p equals one and n equals zero, right? Then around the outside of your hydrogen atom, there is going to be one electron, right? So that's what it normally looks like, right? But if we get rid of this, right, then it has no electrons. And so then it would be fully happy, right? It'd be totally bonded, be good to go. So if we take that away, then we did it. We were happy, right? We have a happy hydrogen that doesn't have to figure out how to balance its electrons. We could alternatively also add an extra electron right there by gaining an electron, right? But this doesn't happen. It's not possible for hydrogen to support two electrons. It just doesn't happen. Okay, hydrogen's a little bit weird. It breaks some rules, but I wanted to show you this one in the first place. So if we can get rid of this electron, hooray, we did it. Now we got rid of an electron, right? So what's our charge now? We technically have a positive one charge, right? And I always write it like one and then plus sign just because I'm weird, but you can write plus one, doesn't matter. So the ion that we're dealing with here would be hydrogen one plus, and it would have zero, zero electrons, right? So this is the ion for hydrogen. This is how you get hydrogen happy. Hydrogen is going to be a positive ion, right? And actually, let me go down the table here. Everything in this first group, because groups are the vertical column, everything in this first group is going to have a plus one ion. Everything in the second group is going to have a plus two ion. And I'll show you an example. Let's do beryllium. Okay. So let's get beryllium out here and we'll take a look at what beryllium is doing. Okay. Sorry, I totally goofed that up here. If your charge is negative, then you're going to be adding electrons. There we go. Okay, cool. So let's look at beryllium. Okay. So if you look at beryllium, normally it has a value of 9, right? A equals 9, right? And Z equals 4, which means we're going to have 4 protons, and 4 plus 5 is 9. So we're going to have 5 neutrons. And how do you make this balanced? If these are positive, you need to have 4 electrons. Whoa, wrong color. My apologies. 4 electrons. There we go. Okay, cool. So then if we make our atomic Bohr model here, we're going to have P equals 4, n equals 5, right? And then remember the first energy shell gets 2 electrons in it. 1 electron, 2 electron. That's 2 of our 4 electrons. And our second shell is going to get 2 electrons in it. Remember, we do it in a around the outside 1, 2, 3, 4, 4 corners approach. So we would add extra electrons here if we needed to, but we can't because those don't exist on this particular model. So there we go. That's our happy beryllium, right? Well, that's our atom of beryllium. Now, in order for beryllium to become an ion, what it wants to do is it wants to have a happy shell. So, how can you make the outermost shell either completely full or gone, right? Because if you eliminate these electrons, then that shell no longer needs to exist. And what's the new outermost shell? It's this first shell here. And isn't two a happy shell? It is, right? So the question you have to ask yourself each time you look at these things is, okay, is it going to be easier for me to empty the previous shell or the outermost shell or to fill it? So let's go back to our beryllium and look at it, right? So if we wanted our beryllium to be happy to have its outermost shell filled, we could add. I'm going to use a different color for this. We could add one. Wow, that's like completely illegible. You can't see that. Let's use a different color here. Let's use gray. You could add one, two, three, four, five, 6 electrons. You could do that. That would be beryllium 6 minus, right? You could do that. That would make it happy because you'd have 8 electrons in the outer shell. But that's harder. That's hard work. What if you just deleted 2 electrons? Like, boom, these went somewhere else. So if those electrons left and they went and visited some other atom, like they got moved to another place, right? Then our outer shell's now gone, and our next outermost shell is happy because it's got its full complement of electrons that it needs. How many electrons did we take out? We took out 2. So the ion for beryllium should be 2 plus because we removed 2 electrons, right? So how many do we remove? 2. What's the charge now? Positive, right? Because if you look at these electrons, there's 2 electrons and there's 4 protons. 4 is 2 bigger than 2, which means, let's change this to a 2 as well. Now our beryllium is an ion. This is going to be how it works for everything in this group. Beryllium, magnesium, calcium, strontium, barium, radium, all of them, their ions should be 2 plus. So if you look on the left side, these are all going to be positive, and what we call our positive ions over here. So positive ions are called cations. Let me help you remember this. Cats have paws, and paws are positive. Okay, good. Are your eyes done rolling? Awesome. Love that. Okay, that's what a cation is. Okay, so let's keep that in mind. So obviously, there's also going to be a negative ion, and we're going to talk about what those are here in a second. Okay, so let's do an example of one of those for you really quick. But hopefully, you see how this works, right? So, looking at your periodic table, we can give away an electron here, and it's easy. We can give away 2 electrons here, and it's easy. Now, pretend this middle section doesn't exist for right now. Okay, we're going to jump across to boron. Boron is going to have 3 electrons in its outer shell. It's still easier to lose 3 electrons for boron than it is going to be for it to gain 5 electrons. So boron and its entire column, its entire group 13, these are going to also form positive ions. So if we go to our example periodic table here, I'll give you some cheat codes. Are you ready? I'm going to do it in big flashy red. +1, +2, +3, right? Okay, do you get it? +1, +2, +3. Okay, those are the ones that are going to make cations. Now, we are going to ignore this column for now. We're going to do it last because it's the one that's at 4, and that means you could remove 4 or you could add 4, and it would be the same amount of effort. So we're going to talk about this one because this one is special. Okay, that one's special. So special that I can't write legibly what the word special is. There we go. Boom. Okay. Now, what do you think that means about these guys over here? Right? Let's go and look at it. So let's look at fluorine. We're going to go look at fluorine really quick. So let's do the fluorine example, and then you'll hopefully see how this works. Okay. So let's jump right into fluorine here. So fluorine, and let's look at our periodic table, gather our information for it. Fluorine has an atomic number of 9 and a mass number of 19. Okay. Which means 19 goes up here, which means it's going to have 10 neutrons. Hopefully you picked that up, right? So that means we're going to have 9 protons. We're going to have 10 neutrons. Whoa, the color didn't change. Apologies. 10 neutrons. And how many electrons should we have in fluorine? We should have 9 electrons, right? Because our electrons and protons need to balance in order to make this thing the right charge balance. So P equals 9. N equals 10. And then we know the first energy shell gets 2 of these 9 electrons, right? So we'll pop 2 of them in there. 1, 2. That's a happy energy shell because it can only hold 2. Then the second energy shell can hold how many electrons? 8, right? So, whoa, my bad. Add 2 in there. 3, 4, 5, 6, 7, 8, 9. So there's literally just one hole, right? There's one hole right here. If we could fill that with an electron, fluorine would have two full shells. It would be considered happy. It would be satisfied with things. Okay. So if we add this in, then we've now got fluorine 1 minus, right? Because now we've got how many electrons? We now have 10, right? Because we have 2 on the inside and 8 on the outside. So we now have 10 electrons, which is one bigger than the 9 protons. So now we have a 1 minus fluorine ion. Now, that is true for everything in this column, group 17. These all form ions that are 1 minus. Okay. Wow. Apologies. Let's go and look at our video. Here we go. So we're going to go ahead and we're going to change to a different color here. Let's write 1 minus, or we'll just write, we'll, we'll write -1 to keep it consistent. So that's going to form -1 ions, right? That also means that these are going to form -2 ions and these are going to form -3 ions, right? Because these guys in these columns can easily gain electrons to get a full complement. So they want to be the same way as these noble gases here, right? So all of these elements want to seek the same orientation, the same formation as these noble gases with a full outer shell, right? So lithium has 3 electrons. If you ditch one, it has the same shape, it has the same electron configuration as helium, which makes it happy, which makes it non-reactive, right? It makes it a happy, stable thing. Okay. It doesn't have these electrons to have to worry about trying to balance them out, right? So if it ditches an electron, it's happy. Fluorine, if it gains an electron, it becomes the same electron configuration as neon, which makes it happy. Oxygen, if you gain 2, then you're neon. If you gain 3, not that you don't become neon, but you have the same electron configuration as neon, right? The only way to become neon would be to add extra protons and neutrons. Okay. So that's the cheat codes for how these ions work, right? So if you look at anything in especially these first 3 periods, it's technically true all the way down in these columns, and it's true all the way down in these columns, right? There are some special cases in the middle section of the periodic table here, especially in this column right here, group 14. Group 14 is special. It's special because carbon, which is really important atom for life, right? Carbon is like the building block of life, right? Carbon forms a 4 minus ion, okay? But silicon forms a plus and germanium forms a plus. We're not going to worry about what tin and lead do because they actually break the rules quite a bit. So things don't work exactly perfectly once you get down below this level here. Okay. But we're going to focus on just the first 18 elements for the sake of what we're doing. Okay. We're going to focus on the first 18. I might bring these guys in too. We might actually do the first 4, but we're going to ignore these pink metals. Okay. The transition metals, we're going to ignore those for now. Okay. So when you go ahead and you make your ion chart, you just need to know these things. So let me just give you the information one more time so that you know exactly what I'm. The big thing that I left out here is that silicon is 4 plus and that germanium is 4 plus as well, right? So your formation, your electron configuration for these ones is going to be different, right? So plus, remember, what are they going to do? They're going to lose electrons. And minus, they're going to gain electrons, right? So carbon can gain 4 additional electrons, which means carbon wants to bond with pretty much everything. That's what makes carbon a good building block for life because carbon's like bond with me, dog. We're bonding. Now, what's a negative ion called? It's called an anion. And an easy way to remember this is an ion. A negative ion. A ion. A negative ion. anion. Anion. A negative ion versus cation. Cats have paws and paws are positive. Oh my gosh. All right. I'll be here all week. Okay, so let's get you into this then. So what I want you to do is on the same paper that you guys were working on last week, and you might need to write these on notebook paper as well, or not last week, but last lesson. You'll see there are ions for these elements. The first one is sodium. The second one is magnesium. You've got boron, carbon, phosphorus, oxygen, chlorine, argon. Right. Just make the ion chart for those. So what's the ion going to be? And then figure out all the normal stuff. So the same stuff is going to be true for it, right? So the atomic number, mass number, protons, and neutrons should be the same. What's going to change is the number of electrons and the number of valence electrons. And then you'll circle whether it's a cation or an anion. and then you're going to draw the structure. And again, you're going to want to do these on, you can draw these on notebook paper. You can just make the whole thing on paper. That's fine. And then just snap a picture of it and turn it in. Okay. So that's kind of how you're going to do your work for this week. Good luck with that. And then when you guys get to class, you're going to work together with Mr. Roberts to do this for the entire set of the first 18 elements. Okay. So that's it. Thanks for watching. Hope it was easy. Hope it made sense. And good luck.